All right, so this is what we call a wireframe model. Physically in engineering, they actually used to create wireframe models. Have you ever seen these? Where you literally have a piece of wire that connects like nodes and literally looks like a wireframe model because it's made of wire, right? So this is a digital representation, or actually a mathematical representation of the corresponding digital idea that would be used to encode the physical wireframe model. Has anybody been to the Academy of Sciences? Have you been to the earthquake section? And you can shake that little thing, and one of them stays rigid and the other one goes like this? That's called eigenvalue analysis, structural eigenvalue analysis. Those are physical wireframe models because these are made of like steel, and the little joints are just welded pieces of steel, right? And that's called structural integrity calculations. Yeah, we'll do more of that in a second. The last thing that I wanted to do was actually what we called, instead of a 3D wireframe model with edges, I wanted to do a 3D wireframe model with polygons. So this is example 3.1.5. Let's create a 3D wireframe model using polygons rather than lines. What do I mean by that? Currently, if we looked back at that example, this whole geometry is created by two different concepts. The concept of a vertex and the concept of an edge, which is just a line segment between those two vertices. Which means that every edge has exactly how many vertices? 2. Right? Every edge correlates with there's a start vertex and an end vertex. But we just said that in this particular model, if we're going to create visuals in R3, we might say that we can create really, really complex geometries out of triangles. Well, each triangle we could call a polygon. Poly means many, gon means gone. Gon means side, right? So many sides. What's the simplest polygon that you could ever study in geometry? Triangle. So why don't we say, instead of encoding edge tables to be lines between this, why don't we require every quote-unquote edge, instead of being a line segment, is actually a polygon, which means each edge corresponds with how many vertices? 3, which means we can then construct entire surfaces out of sets of triangles. Okay, so let's do that. How would we encode the exact same pyramid instead of with a 3D edge table? We'll call it a 3D polygon mesh. Oh God, yeah. I'll call it face table for now. Because instead of everything representing an edge, every one of those would represent a face, right? Could you guess how many faces I need now? Just count them. Yep. And we'll say first vertex, second vertex, and then third vertex. And then perhaps you could actually do this for me. So instead of requiring me to do this for you, maybe you could just read them off for me. And Omar, this actually starts to answer your question a little bit. How do you enumerate? What rule do you impose to enumerate? And I might say, why don't we impose the rule that just, if possible, use the smallest possible index to create those vertices? Do you have to do that?
My real question was why we have triangles instead of squares at base, but then might help me realize
cool.
that we're modeling with triangles only.
Yeah, and why would we do that?
Simplicity.
Because you can build squares out of triangles, but there are some situations where you, like, how would you do this if you said the fundamental concept was a square? How would you do the one between V2, V3, and V5? Could you do it? I mean, I guess you could create a larger square and then cut it in half, right? But it gets kind of ugly, right?
Yeah.
Whereas if you allow your fundamental concept to be a triangle, you can make anything out of triangles. You can make hexagons, you can make octagons, you can make circles, right? They're kind of squared circles, but they're still circles nonetheless, right? Yeah. All right, so let's go ahead and do this. Let's start with face number, and let's say that the lowest face number is associated with vertices with lowest index. Okay, so face 1 would be what? 1, 2, 3. Face 2? Maybe we say, if it involves 1, let's go ahead and capture it, right? 1, 3, 4. Okay, face 3, 4, 5, 6. Okay, what's the next one?
1, 2,
Yeah, we might say 1, 2, 5, and we'll just order it going upwards. What's the next one?
2, 3, 5.
Yeah, 1, 4, 5. Now what?
2, 3, 5.
Yeah, do you see there's kind of a rhythm to this?
3, 4, 5.
Yeah, 3, 4, 5. So that was my thing that I was trying to say earlier, Omar, that if I just label it like this, I'm sure not to miss anything, right? I just look at the smallest index that's been covered, look at all faces connected to that. Once I'm done with that one, move to the next one, look at all faces connected, and then just move down from that. All right, now we have a concept of fundamental concepts in computer graphics, how to construct this. Let's see what some people have done using this idea. And maybe we can convince ourselves that, whoa, this stuff is not as trivial as we might believe it is. Let's see, escape perhaps. All right, so there's a visual in Mathematica I used to graph this thing. We saw this last time, and the claim is if you zoomed in on this, my claim is this is literally a set of triangles. Some of you might use SolidWorks. That's a question.
Yeah.
Then you're used to this, right? Yeah, so if you zoomed in on this thing, I think this is some sort of a crazy Lamborghini, right? Do you see the triangles? Do you see them? The squares, well, what's a square? I would just go back to Omar. What's a square? 2 triangles, right? There's triangles on the surface there. Of course, car windshields are rounded, but in computer graphics, I could do rounding in 2 steps, right? The first step would be to create the structure, and the second step would be to render. So instead of using lines, I could use quadratic or cubic functions so that my vertices are connected by something that looks smooth. That's what GPUs do. GPUs allows you to take your vertices and then make nonlinear connections, and then as you move it around your space, it just makes sure to keep the connections well, which means you have to calculate all over the place, right? All right. So that's an example of a car that's made in this same fashion. Of course, there's data structures underneath, so let's not assume that linear algebra is just as easy as writing these things down and then all of a sudden you get stuff like this, right? You actually have to do some work here, which is applied math, which means you have to bring in some other stuff, like computation, for example. And then we talked about this. This is Stanford money that models, or that kind of is a really famous visualization for model order reduction. Claim the thing on the left is a set of vertices and a set of triangles. The thing on the right is definitely a set of vertices and a set of triangles. They look really, really similar. That thing has millions of vertices. This thing has like tens, right? Which is kind of cool. So that's currently the state, a major state in linear algebra is how do you work with stuff that's really, really large and not actually have to use it to compute? That was my PhD thesis, was all about that, right? How do you work with matrices that model systems that have millions of components without breaking the computer that you're working with? Well, there's a few different ways to do that. One of them is to lessen the components that you start with. The other one to do it is to capture everything and then reduce the order of the model so that the stuff that you calculate on is a lot less than the stuff that you want, and then just make sure that the correlation between the two of them is quite strong from the standpoint of computation and error, right?